So this is what the session is going to be. It's Hello World, right? How many of you have written a Hello World program in C? Everyone. Wow, that's awesome, right? So what we're going to do is we're going to write Hello World again, but then we're going to take a slightly different look at it, right? We look at Hello World in a programming language, and then we move on to writing more complex programs, right? Sorting, linked lists, etc., etc. We're not going to do that. We're going to look at Hello World and try to see what we get that runs on a computer, right? So the theme is quite literally to bring back the C in CS. We look at computer science, we look at different subjects like computer architecture, operating systems, and so on, and we deal with them in silos, right? You did computer architecture in first year, did you? Right. Second year, right? I did not do computer engineering, as you have realized. What about operating systems? Third year, okay. And programming languages? Second year, okay. What about system software? In general, linkers, loaders? Third year, awesome. Do you know all these three, four things are related? How? Anyone wants to give an idea of how they are related? That's fine. We'll look at it now. Okay. So we're going to look at how all of these things fit in, okay, in practice, in real life, and we're going to get a concrete view using your computers. So how many people over here don't have Linux on their laptops? Everyone has Linux on their laptops, right? If you don't, team up with whoever has Linux, because we're going to use Linux almost exclusively to do all of the examples, right? And most importantly, ask me anything. Okay, I work in the industry, I work in compiler technologies, so I can give you as detailed a description as possible of the kind of work that we do and of the kind of work that my peers do in these technologies, right? So Abhijat sir already mentioned all of this, so I'm not going to repeat that. And next slide. That's it. There are no slides. Okay. So let's get back onto our computers. And what I'm going to do now is get rid of the slides because we don't need it. And here, what is this thing called? It's a terminal. Awesome, right? So the first thing I want you to do is type out this program. And you will discover that I don't know how to type. So this is a program that you need to write. Okay, type it out on your laptops. You can see it, right? What does the program do? Prints hello world. What are you saying? What does it print? Hello world. That's what I'm saying. Hello world. No? Okay. So just print this out. You can print any other. You can print a more optimistic hello world if you want, right? That's what we are used to. And once you're done, I want you to do this. GCC. How do you compile the program? File name .c. That's it. And what is the output name? File name. A.out. So all of the programs that you see in the industry, are they all called A.out? No, right? They have a file name. They have an output program name. So always get into a habit of providing an output program name. Always. Okay? As in, even if you are writing a test program, this is how you should do it. Okay, forget that. So A.out is outdated, as in it was a binary format that was invented probably in the 60s or something like that, and that binary format is not even used today. And if you're wondering what a binary format is, we'll probably talk about that later. If anyone's interested in knowing, note that down as a question and ask me later. Done? Oh, you're very fast. That's very good. So did you compile the program? Right? And what happens when you run it? Does it do this? Okay. Anyone who's struggling with it, anyone who's not able to compile this, everyone's able to compile this, right? Okay, great. And you get the right output. Okay. Now, when we did this, when we compiled this program, do you know how many steps of operations happened underneath? Take a wild guess. System Software 101. Pre-processing. After that, compilation, assembly, linking. Wow, okay. This is a very, very smart crowd. You'll know like all of the 4 steps, right? So now what we're going to do is go through all of those 4 steps one by one, okay? Did you know that you can actually do that in GCC? Yes? Awesome. So what is the flag to do that? Minus S? What does this do? Assembly. Okay. But then was that the first step? Somebody said pre-processing, right? Yeah. So the first step is pre-processing. How do you get pre-processing? So that's minus E, capital E. Okay. So try this now. Okay. And name the file name hello.i. Okay. I is a standard extension for pre-processed files. Okay. So what do you expect as the output of the pre-processing? Expanded source code. So when you look at this source code, how much more can this be expanded? Is there, this is a very small program, right? How many lines is this? 1, 2, 3, 4, 5, 6, 7, 7 lines. 800 and? That's hello.i, right? What the hell is all of that? Hash include. So what does hash include do? Again, as a chorus. No, one of you. What does hash include do? Includes the header file. What does inclusion actually mean? Redefine. No. Okay, what is that predefined code? Now, okay, there are a lot of abstract concepts. This session that we are doing is going to be very, very, very concrete. So unless you are concrete about what you mean to say, I'm going to keep asking that question. You're right that it includes some predefined code. What is that predefined code? Where is it? How is it included? Printf. What about printf? The definition of printf. Okay. Somebody said declaration of printf. Is it declaration or definition? Are they the same thing? No. Okay. So it's a declaration of printf that you want, right? But then does stdio.h have that? It has all the declarations in the world. Declaration of printf. Right, right, right. Now, how does stdio.h get included? We are back to the same question. What do you mean when you say included? Only the? So the answer is going to be so stupid that you'll probably laugh. What is that? It'll copy the contents of stdio.h and just paste it on top, right? That's exactly what it does. It just opens stdir.h. Where does it open it from? Main folder. What is the main folder? Which library? And what do you mean by library? we are going to get answers to all of these questions. If you don't, somebody please note them down. If you don't get answers to any of these questions, ask me later. What is a library? Okay, that's one outstanding question that we'll keep aside for a while. Right? So where is stdir.h? The question has not been answered yet. The GCC include folder. What is the GCC include folder? Is there something called as a GCC include folder? There is, but stdir.h is not in that. User include. Awesome. Right? So you have a directory called user include. This is the default include directory. This has a lot of header files, right? And these header files are not necessarily, in fact, most of them are probably not from GCC. Okay, they are from a library. Most of them are from a library called glibc. Okay, is a standard C library. We'll keep hearing this name again and again, and I'll probably delve deeper into that project as we go ahead. Right. So now we know where stdir.h is. Right. Is it in that directory? Let us confirm. Yes, it's there. Right. And if I open it, I can actually read it. Right. There's a bunch of things in there. So now we know exactly. Now we can very concretely define what pre-processing does. Right. We see stdir.h. The include, and we pick up that file, expand that in there. Now we look at that entire file again. Are there any other includes? Are there any other includes in stdir.h right now? There are, right? There's bits types file, and libio, and so on and so forth, right? So recursively, it will open that file, right? That is one aspect of pre-processing. The other aspect of pre-processing is macros, which is like a minor language by itself. If not defined, then define a macro, you know, and then there are other macros which allow you to paste strings together and all. So it's a very small constrained language which does a limited set of things, but it allows you to, it gives you a very powerful mechanism to conditionally compile code, right? For example, if you are doing stdir.h include, let's say you include another header which also includes stdir.h. What happens then? You include stdir.h twice. Is that a good thing or not? No. So there is a very simple mechanism which says if not defined macro, define that macro. Okay, and everything else happens if that macro is not defined. What that does is that if you include stdir.h the second time, your contents won't get replicated. You get all of those declarations exactly once. Okay? So this is the essence of pre-processing. Now let's take a look at the pre-processed file. As you can see, it's 844 lines long, right? Where is your code? It's buried right at the end. Those your 6-7 lines are buried right at the end, right? And what did we need all of this for? We needed it for, why did we need stdir.h? For printf, right? For the printf declaration, so that we can tell the compiler that I'm calling this function printf, and the function has the following parameters, and this is what it returns, right? Let's look for the printf declaration then. I want you all to do that. Look for the printf declaration in there. So I found dprintf, vdprintf, vsn printf, sn printf. There. This is printf. Did you find it? Okay, anyone who's having trouble finding printf? For minus capital E. Capital E. That's the switch. Everything else remains the same. Yes. Everyone found this? Okay. So now you know that just for this one printf, we included 840 lines, right? So can we drop everything else, just keep this extern int and build the program successfully? Or will it fail for something else? Is there some other mysterious feature that stdio.h adds that we are not aware of? Or is it capable of doing that in the first place? How do we find that out? How do we find out whether this is sufficient or not? We delete everything, we keep this in place, and we compile it. It works, right? So let's try that. If any of you is lagging behind, wants me to stop to catch up, just let me know, okay? So I'm going to open this, I'm going to turn syntax off so that I can actually see something. Oops. There you go. So I keep printf and this. Okay. So this is going to be my new C source code. I can keep it as .i, it doesn't matter. Okay. We'll take a closer look at the function later, the declaration. Now if I say gcc minus o hello, hello.i, works? Okay. This works perfectly, right? So there is nothing else that a header file adds other than declarations. Okay. So as such, if you're looking at any program, if you're able to remove all of the cruft, so the other 800 lines that you saw, 840 something lines, they were all cruft in the context of this program, right? So you could have technically just written this program and that would have been sufficient, correct? Why don't we do this? Why don't we do more of this? Any guesses? Your guess could be wrong, that's fine. Why don't we just always write extern int printf and whatever, and why do we include 800 lines of cruft?
Every time writing is not feasible and remembering also.
Why is it not feasible? I'm writing a hello world program, this should be fine, right?
But every time you have to remember that printf declaration and printf declaration.
Okay, so you're kind of on point. What happens is that you're not going to write hello world all the time. You're going to write something that is a lot more complicated. And there are a few thousand library functions in the C library. And if you're going to write externs for all of those, that will take up a lot of your time, and in most cases you'll be wrong, right? You'll make mistakes in that. So that is the reason why you don't do this. But then this is important to know, right? Because now you know that the only reason you have the header file in a hello world program, the stdio.h, is for the printf declaration. There is nothing else that you need over here. Absolutely nothing else. Let's modify the program a little bit. Okay. If I say size t foo, because I don't know a better variable name, I'll just there. Size t foo equals 42. Okay. And what is the format specifier for size t? Percentage ZU. Okay. And I print foo. I'm not going to compile this, but tell me, will this work? So, to understand whether this will work or not, you need to become the compiler and see what the compiler sees over here. The compiler sees this in this program, it sees main as a symbol. It is a function definition, correct? A function definition it can handle, because it is just going to build a tree for it and generate assembly for that. That is perfect. Now, you have foo, which is a type, which is of type size t. Then you have printf as a function, right? And at this point, it is going to start wondering what is printf. And then you give it the declaration, correct? And then it says, okay, there is a declaration that tells me what printf is. That tells me that the arguments that printf can have and the return type that it has, that it returns, right? So, printf is also sorted. Return is a keyword, so I understand return, right? And return a constant number, correct? So, now I have compiled everything except size t. Now, it all depends on whether the compiler identifies size t as a type or not, okay? And the compiler does not. The compiler does not identify size t. Size t is provided by a different header, which is essentially a type def. Okay. Now, have you ever seen size t as a type before? How many of you have not seen size t as a type? Most of you, right? So, I will just tell you what size t is. Size t is the size of a pointer, essentially. Okay. There is a ptr t which is precisely the size of a pointer, but then size t is unsigned long for that machine. Now, if you are on a 32-bit machine, it is different. If you are on a 64-bit machine, it is different, correct? That is the reason why you have a standard type called size t, which will differ from machine to machine. And it is glibc which will look at the machine and it will provide you macros which will say for a 32-bit, for a word size 32-bit, size t is 32-bit, for a word size of 64-bit, size t is 64-bit. Okay. So, you need to provide a type def for size t. Okay. So, you quickly realize why you need those standard includes. It is because you do not want to do work that is unnecessary, right, when you are writing large programs. But then if you are writing embedded programs, if you are writing compilers, if you are writing low level runtimes, you might have to end up doing all of these things, right, especially when you are doing very early initialization. Do you understand what I mean when I say very early initialization? I am guessing not, but you will in a while, right. So, now we have pre-processed a program and we have our pre-processed code. Next thing we will do is generate. What do you get after that? Assembly, right? Okay. So, let's exit this. I will generate hello.i again. This is how I generated hello.i. Now, from hello.i, how do I generate hello.s? You already told me this, right? It is minus capital S, correct? So, now let us look at our assembly. Now, this is fairly straightforward. I think all of you must have actually seen this in some form or the other at some point, right? How many of you over here are comfortable reading assembly? 1, 2, okay, fine. So, do you know what this is doing? What is CFI start proc? Oops. Okay, let us go from the first line. So, first line, what does it say? The file is hello.c. So, these are called assembly directives. Okay. So, and then it tells you it is in the .text section, and then there is read only data, and then you have a function, right. Now, let us go through the function. What does it do? It pushes the which register is this? Base pointer, right. So, this is which architecture is this assembly for? 64-bit what? What is the CPU? It's an Intel 64-bit processor, right? Now, this is very important because there are, so you need to appreciate the fact that there are probably a dozen or more different CPU architectures out there. Okay, Intel is just one of them, right? If you're going to work in the server world, you'll probably mostly only deal with Intel servers and desktops, right? That is slowly changing. You are getting desktops with ARM architecture CPUs as well now. Your Chromebooks are all ARM architecture CPUs. Your phones are all ARM architecture CPUs, right? They can be 32-bit or 64-bit. So, first thing that you should think of when you are looking at assembly file is what is the architecture? You know why? There is another reason for it, because assembly programming is hard. Assembly programming is very, very difficult. That is coming from a person who has done 7 years in assembly programming, right? It is very difficult and you are not expected to know instructions by heart. You need to pick up a manual. So, the first step when you look at this is, okay, this is Intel x86-64, let me pick up the Intel x86-64 manual, okay, and then start trying to figure out what it means. Okay. But then there are some primitives that are always there on most processors. So, you know that push means push onto stack. Okay. What is a stack? Stack is memory. It's on the RAM. It's a location on the RAM, right? So, we'll see precisely what the stack is later on. Okay. So, it pushes on the stack. Then you have move from stack pointer to base pointer. So, you move your, you preserve your stack pointer. Then you move a certain return address, I am assuming, yes, it should be a return address to, no, where is that? To this register called EDI, and then I call this function called puts. What is puts? Have you heard of the puts function ever? Input, output. So, I know it could be input or output, nothing else. So, is it input or output? Output. Okay. What does it output? A string, right? But then where does this come from? We wrote printf, right? So, where did this come from? Where did puts come from? Okay. Hold on to that question. The next thing we do is pop the base pointer, which means the base pointer goes onto stack and then we return. Okay. Now, one very interesting thing over here is all of these instructions. In many ways, we did not do this. Did we? No. This was something standard that the compiler added. Okay. And this is called a function prolog. Okay. And at the end of the function, I pop RBP. Okay, the CFI directives we will probably not talk about it. If you are interested in knowing, we will talk about it later. We pop RBP and then we return from the function, correct? So, these two things they are called the function prolog and the epilog. They are standard for every function that you define. Okay, every function that you define, it would be a standard, and it would be a standard for every architecture. So, this is the prolog epilog format for x86-64, okay, where it is necessary to save the stack position into some register, and at exit you pop that stack pointer, right. On ARM it will be slightly different, and this standard interface, it is called an ABI. That's called an application binary interface. It is published by the hardware manufacturer. So, Intel will publish an ABI saying that this is how you call a function. Okay? And now you look at puts. You pushed a pointer into EDI. Okay? EDI is essentially RDI. The 64-bit equivalent is RDI, and then you call the function. This is also part of the ABI. Okay? It is basically telling you how do you call a function. So, the way you call a function on x86-64 is you put your arguments, function arguments in registers RDI, RSI, R10, R9, R8. Okay, don't tell me why it is R10, R9. Don't ask me why it is R10, R9, and R8, and not R8, R9, R10, or whatever. Not a sequence. That is an architecture decision, right? That they won't tell us exactly why. We can make guesses, but that we can talk about later, right? But then that is a standard format. Why would you need such a standard format? So, when you are writing software, right, you might be writing like a plugin, correct? Do you know what a plugin is? A plugin is a library which provides a set of functions, right? Now, when you have to call those functions are not written in C. They were written in C maybe at some point, but they were compiled into a binary machine code, essentially assembly, right? If you are looking at the human readable aspect of it. Now, when you are calling a function in assembly in machine code, you need to know which registers your arguments go into. You need to know how to actually invoke that function, right? Call is one way to do it, but how do you provide the arguments? So, there is a predefined way to do that. So, on x86-64 it is RDI, RSI, R10, R8, R9. On 32-bit it is pushing arguments onto stack. On 32-bit there is also a fast call method, which is I think EAX, EBX, ECX or something like that, right, where you put arguments into those registers instead of pushing onto stack. Why is it a fast call method? Why is it faster putting on register than pushing on stack? You're putting into memory instead of direct register access, right? You're actually going from that chip die, from the CPU chip die, you're walking all the way to the DRAM, pushing words on there, and then you're coming back and resuming execution, right? So, typically if you look at it in CPU latency terms, putting into register would be what, 1 cycle, and going to RAM and back is 400, 500 cycles, right? So, these are things that you need to consider when you are designing an ABI, right? So, now any questions on ABI so far? Mnemonics, in what sense? The instruction mnemonics. So, the instruction mnemonics are part of the instruction set. Okay. So, your instruction set defines what instruction you can execute, right, and then you will have a register file which tells you the register names and so on and so forth. So, with that you can design whatever the hell you want. ABI is just a conceptual limitation where you say if you want to call a function, you have to set it in this way. Now, if you are writing a program in assembly and if you are going to never call any function on the outside, then you can design a faster ABI for yourself within, where you can say that all my function calls, let us say for some reason pushing onto stack is faster for you, okay, for whatever reason. So, I am going to push only onto stack, I am not going to use up registers. Let us say there is very high register pressure, like in 386 machines, right, the 32-bit machines. So, you can make that decision by yourself within yourself, right. The fast call method is essentially that. The fast call ABI for 32-bit is essentially a contract within glibc where we say within glibc we are going to use fast call for function calls because we want to optimize. We don't do that for any function calls that are outside of glibc. Okay. So it is basically it's an artificial contract. It is not a machine limitation. It is just something that you put in there so that you can talk to programs and libraries that are written by anyone else in the world. So it's a standard that you arrive at. Okay. Any other question? Okay, great. So now we come back to the question of what is puts and where did puts come from? We wrote printf, right? Let's take a look at our program again, just to be sure that I did not trick you. It is printf, right? Correct. Now, one way is that there could be an alias. So, the C program in stdio.h, there could be a hash define saying hash define printf puts. Is that possible? No? Why is that not possible? I can't hear you. It's predefined, but I could predefine it as a macro, which is essentially puts. It may be ambiguous. Okay, so let me just first look at the man page for puts, okay, so that we know what we are talking about. So this is our man page for puts. What is puts? Puts is just a file point, a string and a file pointer, okay, which is your stream std out, right? And so sorry, that is f puts. So you have puts where the stream is implicit, which is your standard output. Okay, so you are essentially providing only the string, which is what is happening, right? You have RDI, EDI, which has the string pointer. That's it. We are not actually looking at anything else. So how is this different from printf? So printf, oops, right. So printf also takes a string, but it's a format, and then there's a variable number of arguments. Okay. Now what happens if there are no arguments to printf other than just the format? Similar to, it's identical to puts, right? It is identical to puts. Okay. Now with printf, okay, now I'd like you to take a leap of faith and imagine how puts might be implemented versus how printf might be implemented, okay, in the context of printing the string. How would puts be implemented? Consider the string as a character array, and it will go print character, print, found a null character, return, right? That's how puts works. How would printf work? Right. Correct. Then it will start printing, right? So there's this whole lot of processing that happens first, and then there is a printing phase, right, with printf. Whereas puts is just blindly print, correct? So which is going to be faster if you have to print just the string? Puts, correct? So and this is a very straightforward, unambiguous optimization. Okay. Now who has done that optimization? In this, who did that optimization? GCC did that, right? Oops, what did I do? There you go. So GCC did that optimization. So GCC optimized a printf with just one argument into puts. Okay. This is one of hundreds, if not thousands, of optimizations that GCC does. All right. And I think next week in Uday sir's sessions, you'll probably take a deeper look at how these optimizations happen. So a lot of them are mathematical transformations and analysis, right? Data flow analysis. But then there are these little gems that actually come from the industry in most cases, because there is where they are looking to squeeze that last 1% out, and this is how people squeeze the last 1% out when it comes to optimizations, right? Then there is if you have like multiple function calls, which could like for example string n copy versus string copy, there could be transformations in there as well, which allow you to choose the faster routing, right? So GCC does that, and GCC only generates assembly. Okay, GCC does not produce object code. All right. There is something called as fdump tree and fdump RTL arguments to GCC, which allows you to analyze the various passes inside GCC when it comes to optimization, but I won't go into that again. That you'll probably learn a little more later. So now you have the assembly file. Is this executable in the machine? No. So what do you need? Binary. So let's zeros and ones. Let's get the zeros and ones out. So what is a program that you would invoke for this? Okay, let's not go into the assembler. Let's allow GCC to invoke the assembler for you, right? So how do you do it? -c, right? hello.o, okay, because O is a standard extension for object formats on Linux, right? So I am compiling only. So this is only compiling into object code. We are not doing anything else. And if you look at large complex projects, this is a command line you will see very, very often in makefiles. Okay, you will be compiling lots of code into object files, and then you will be combining them into executables and libraries. Okay. So did you see this? Now, how do I see this object code to see what's inside? Can I do less? Is this possible? Let's see. Whoops. What is all this? I don't remember writing at the rates. That's not right, right? So it is a binary format, correct? So how do I analyze the binary format? XXD or hex dump, basic XXD, is it? Okay. This. Now what do you get, what do you understand from this? Right. So let's pipe it to less. Okay. There is still things that you can understand from this because of the strings in there. Like it tells you that the first 4 or 5 bytes tells you that it's an ELF file, right? And what is an ELF file? So ELF is called the extensible and linkable format. Okay, it is a format. It's a binary format for any program. Okay, so it could be a library, it could be a binary, it could be intermediate object code. Right? It is an extensible format to define how a binary would be laid out in memory or on the disk. Okay, right now where are we? Are we in memory or disk? We are on disk, right? The object code is on disk. It is not being executed, right? So now we are looking at the ELF format, and looking at the ELF format just like that is utterly useless, right? Because what you have is object code, you have opcodes and all that encoded in binary, and there's nothing you can do with it. So you use a tool called objdump. So in this entire process, I'm going to introduce a lot of tools. Just note those down whenever you're doing them, and explore those tools further, because there's a lot you can do with those tools than just looking at dumps like this. Okay. Now, suddenly you see this, which is so much nicer, right? So So now this is basically assembly code. It has this is called disassembling, right? It has disassembled binary code to show you assembly. Okay, and this is how you can look at the code of any program on your operating system. Any program. So I can use objdump, and what is your favorite program? ls? ls? Okay. So ls is in bin. Okay. This is the assembly code for ls. All of this is assembly code for ls. Now the only thing that you need to know is to understand how to traverse all of this, right? And you shouldn't have to do this because this is really hard. Like I said, assembly code is hard. It's hard to read assembly code. That's why you how do you read ls code otherwise? It's an open source project, right? So it's part of a package I think called core utils. You just download the source code for that package and you read the source code. It's in C. Right? That's the power of open source software. You as a student don't have to pay anyone to do that. You can just download it off the internet and look at the source code. But for anything that does not have source code available, this is one way to look at it. Right? And then when you're doing diagnosis of programs. Right? So this is your assembly code for ls. Like that you can look at assembly code for anything in the world, right, by using objdump. Let's get back to our example. So now your object code looks more or less the same as the assembly code, right? Okay, except that the call is a little weird. It is calling some E, right? Does that even make sense? It calls the next, so E is the address and this is E, the address, which is the next line. Does that make sense at all? It doesn't, right? So this is a placeholder. It is saying call a function. It doesn't yet know what the function is, right? Now, how are you going to tell it what function it is? You use the linker, right? So let's get to the linker. So now you're going to output hello using hello.o. Okay. Now, before you open up hello under objdump, can you guess what would be in that file? There would be main and the definition for main, right? What else would be there? So what do we do in main? Let's look at the program again. What do we do in main? We call printf, the function. So do you think the printf definition would be there in the objdump? Yes, no? There can be two answers, yes, no. How many say yes? Okay. How many say no? The rest, I guess, right? Or is it, I don't know, I want to play safe? Okay, so let's assume for now that the definition is in there, right? And let's go look for it. How do you do that? objdump minus d hello. What is all of this? Okay, where is our main now? Did we write all of this? Did we write underscore init or dot plt? I don't even know what that is. What's puts plt? Puts @plt. There is underscore start for some reason. Deregister tm clones. So these are all function names, right? Deregister tm clones. What does that even mean? register TM clones, do global detours aux, frame dummy main, finally, right? Finally we got main. And what does a call queue transform to? Because that is what we are interested in. What does it transform to? It transforms to an actual address, right? And what is that address in angular brackets? That's puts @PLT. There was puts. We knew puts was going to be there. What is the @PLT? Let's look at puts @PLT. What address is it at? 4003 F0. That is 4003 EC F0. It's here, right? This is puts @PLT. Okay, so you don't need to be a genius in reading assembly code. Okay, can you guess if this prints a string? Does this print a string? Yes or no? Yes, but it is just jump, push, jump. How would jump, a jump, a push, and a jump print a string? So you're jumping to some point, then you're pushing something on. Well, it's literally 0 onto the stack, and then you're jumping again. How does that print a string? What would you expect when you're printing strings? You'll probably expect a move, and you'll expect some other things that we'll talk about later, right? A jump, push and a jump is not a string printing function. Ergo, this is not puts. Okay, this is not the real puts. It is puts @PLT, and we have no idea what that is. Okay, actually, we do have an idea what that is. You must have done this your systems course, and you must have talked about. You must have learned about position independent code, right? Position independent code doesn't ring a bell. Never heard of it? Okay, fine. So when you are compiling a program, you say I want to call a function puts, right? What is a function call essentially? It is a call to a certain address, right? When you are loading that program in memory, you need to know what that address is, correct? For that, you need to know where puts is in your address space. Okay, if you were all in one binary, you would know where that is. You'll find the offset, and you'll be able to jump to that address. If you don't know, as is the case over here, puts is not in here, right? There's only one stub. It's called a trampoline. Okay, there's a trampoline which allows you to jump to push. Okay, so now what the code that the linker generates, it generates a trampoline and a jump to that trampoline, and it says somehow now that is going to result to a jump to puts. Okay, who does that jump? We'll find that out later. You had a question? The question was who does that jump? No, okay, fine, right? So there's another aspect to it. Linking. You must have heard of dynamic linking versus static linking, right? So what do you think this is? How many say dynamic? Okay, and I'm assuming the rest of you all say static, right? So this is dynamic. Okay, the main feature of dynamic linking is that when you're calling a function which is in a different library, you have a trampoline here. Okay, and you don't have the actual function. The actual function might be anywhere, and that is where position independence is required. Okay, and you'll appreciate this much later when I show you how a process looks like in a computer, right? Now, this is dynamic linking. Then let's look at static. Okay, how do you produce a static binary? Okay, before we do that, let's take a look at hello in terms of size. how big is it? It's 8 kilobytes, right? Okay, you're doing that also, right, on your systems. So it's 8 kilobytes. Now let's build it statically. The way to build statically is to use the minus static flag. Okay. Once you do the minus static flag, you look at the binary. What is the size of the binary? It's the same? It's 700 kilobytes. It's 100 times bigger. Right? It's 100 times bigger now. It obviously has 100 times more code. Right? So let's take a look at it. And this time I won't do any gimmicks, I'll just jump straight to main. Oh, by the way, this init and all, I'll talk about it a little later. Here's your main. Okay? And now look at your call. The call is, it's not puts, it's what? IO underscore puts. Okay? The reason why it is IO underscore puts is because that is the internal name for glibc. Okay? So glibc uses the IO underscore puts name so that it doesn't have to jump through a trampoline. If it calls puts, then it will have to jump through the trampoline. So it calls its internal name IO puts, so it goes directly. What is the disadvantage of jumping through the trampoline? It's an extra instruction, right? It's an extra 3 instructions. CPU cycles, right? And in fact, there are other aspects to it as well. Your PLT would be here in memory, your IO puts would be here, and my function call would be here. There is something called as cache locality, right? Whenever you're making a call, you make a call over here, it doesn't mean that this is going to be cached. Only neighborhood stuff will be cached, right? So there are a lot of things that make it much slower to do that indirect jump. So these are called indirect calls. Okay. So to avoid that, we use the internal name. So now let's look for IO underscore puts. Here. Now this is a very, very big function and is much likely to be operand, right? So it's all the way up to here, right? 40841B from 408.140, right? That's a proper massive function that does stuff. So you can, if without actually getting into the assembly, you can assume very safely that this may be printing an array onto a screen, a string onto a screen, right? So now here's the interesting thing. You linked statically, so you got the entire function over here, right? You got the entire function in there and it's there in your binary. Now this binary does not need libc. The dynamically linked binary needed libc. Okay? So the way these programs are executed are also very, very different. This static program and the dynamic program. Right? Any questions up to now? This is all we've done to find out what happens to your C code right down to your final program. Okay? Now we'll look at the program a little more closely. Okay? And to do that, we're going to try and write the smallest program possible. All right? What is the smallest program that you can write? Hello world is obviously not small. If you pre-process, it is 844 lines. What's that? Empty program, just int main, right? So I'll cd into another directory. There you go. And now this is what you're talking about, right? You can return whatever you want, but essentially int main and return your favorite number, right? Do this program and generate a binary. So how do you test the return code that your program is given? It is returning 42, right? So how do you test that? So in shell, once you execute, you have an echo $? Which queries the previous program's return state. Okay? So now you know how to check if the program is working correctly. All right? So now this is a really small program where the first function that ever executes, which is main, right, in your program. That's the first function that executes. It returns 42 and it exits termination. It exits the program, right? That is so simple. It should be, when your compiler is trying to optimize it, it should produce what, 5-6 lines of assembly, right? There should be nothing more than that, nothing at all. Now let's see what it actually generates. So how many lines did it generate? (151) lines of assembly. Right. So to figure out at what stage all of these lines got added, let's first generate only the assembly code. Okay, so this was what our main looks like. Let me just produce the obj dump because it's easier to read. Okay, so this was what we were expecting, right? We were expecting main, and main is the first function that gets executed, right? And that's it, right? There should be nothing else. Why is the compiler, so the compiler is working fine, why is the linker adding so many things? Any clues? So when the program is executing, right, if I look at obj dump, why does it need all of these things? Okay, why doesn't it stick to just main, which I can't even find? Here it is. Right? It is just this much. What is all of the other cruft in there? And is it necessary at all? How many of you think it's okay? How many of you think it's not necessary, and we can get rid of it? It's necessary. You always need that, but main is the first function that executes, right? Yes, everyone agrees. Anyone who disagrees with that? Okay, so now let me break it to you. Main is not the first function that executes in a program. When you write int main, that is just a C language standard that says that int main is where your your business case as such starts and ends. There are a lot of other things that start before that, and as such, for every program there is a symbol called _start, which is the beginning of your program. Okay, again I've lied. _start is where your program starts, but then there is something called as _init, which initialize your program. Okay, so when you look at this, you have an _init, which initializes your program. Okay, it is an initializer. Okay, and then you have _fini right at the end, which finishes off your program. Okay, so there is a more modern concept called init array and fini array, which allows you to provide multiple initializers and finishers to your program. Okay, now if you look at programming concepts, What is a concept that is parallel to this in OOPS? Constructors and destructors, right? So this is essentially your object destructor, and this is your object constructor. So when you're writing C++ programs and you have an object, right, which has to be constructed on program load or whatever or destructed, it will typically have an init array function in there. It will be a function in an init array section, right. So you have your init and fini, your constructors and destructors even in low level programming, because they are necessary to implement whatever high level construct you think of in your program expression, right. And once your initialization is done, then underscore start, and then at the end, once your program is over, fini is called. Now, who calls all of these functions? Right, that is the next question. Who calls underscore start? Who calls underscore init? Who calls underscore fini? We will leave init and fini aside. We will look at start. First, a quick detour for the smallest program that you can write. This is the smallest program you can write. Okay, type this. Right. So all of the spaces that you see are tabs. Okay, your assembler, it doesn't strictly require that, but it's nice to write it this way. And this also introduces you to a new instruction called syscall. And there is no ret over here, if you've noticed. So the first number that you move into RDI, it can be any number. The second number, make sure that it is 231. Yes. It could be properly spelled as global as well. It identifies both. So some crazy person in the 70s decided GLOBL was right, and it is stuck. It's stuck as a compatibility thing. Okay, so how do you build this? Let's build this using the assembler AS. Okay, so we are like completely bare bones now. The next thing you'd be doing is typing ones and zeros. We could actually do that with this program, right? So AS tinyasm.o tinyasm.s, okay, and then LD tinyasm.o, okay. Then when I run my tinysm, it gives me the right output, okay. Now if I look at all of the files, smallest was 7.8 kilobytes and tinysm is just 700 bytes, okay. So that's what we were going for. We were going for a very, very, very tiny program, and we've achieved that with tinysm. Okay, does everyone get this? Anyone who's stuck? Do you need help there? It's done? Couldn't find entry symbol start, right? That's probably because you did not write .global start. This line, let me see. This line. In any case, that's a warning. Okay, so you'll get the final output. Sorry? Dot global. Dot global space underscore start. I'll need to figure out the syscall numbers for it, but so I can tell you the syscall numbers. That's not sufficient. Yeah, yes, that's not sufficient. But then that's a good point. So I'll show you how to find the syscall number, and then you can fix up that program. Okay. So assume everyone's got this. So let's step through the program. Okay. And there's not a lot to step through. There are just 3 instructions. What does the first instruction do? What does it do? Move 42 to RDI register. Okay. That's your function call ABI, right? Except that this is not function call ABI, this is syscall ABI. Okay, the syscall ABI or the system call ABI is different. Everyone knows what a system call is, right? What is a system call? Which system? Operating system. Okay. You were saying something. Okay. Right. So, the way, okay, when you say operating system, you have to be very, very specific. It is the kernel that you need, you're referring to, right? And why do you need a separate system call infrastructure for the kernel, and why can't you do something like a function? Because with libc you can always call a function, right? And the function ABI, function call ABI is sufficient. So why do you need a system call ABI for this? And why do you need a special instruction called syscall for that? System call number is right. We are pushing that number in RAX. See, this 231. There is a system call number which tells you which service I need, right? And then I say syscall. But why do you need such indirection? Why can't you just call a function inside the kernel? Right. No, I'm saying at the ABI level. Why don't you just do call exit underscore group? This syscall number is exit group. Okay, 231 for 64-bit. As she discovered, for 32-bit, it's a different syscall. Okay, so you need to figure out what that is. Right. So why do you need to do that? Why do you need to set a syscall number in RAX and then call a separate instruction altogether called syscall? And why can't you just do call exit underscore group? But what is special about the kernel? Why can't I just why couldn't I just link the kernel as a library and make that call? I am asking you why they cannot be called. I know they cannot be called. Sorry? Privilege level, right. So that's what I'm looking for, right? So whenever you're executing code, you can either execute in user mode or you can execute in kernel mode, right? What is the difference? User mode has a specific set of addresses that it can reference, right? It cannot reference anything outside of it. It basically has an abstraction of its own that it can use for accessing objects. It cannot access anything inside the kernel, correct? So you need to provide a special instruction called syscall. In 32-bit days, it was a proper interrupt. It was int, interrupt number was 0x80, right? And that interrupt handler was written in the kernel that would then execute the syscall, right? It would read the syscall table and execute whatever syscall is required, correct? You need all of that for privilege separation, okay? Now, how many of you are interested in security? Right. So most of your security bugs, when it comes to privilege escalation, is essentially trying to defeat this barrier. Okay. How many of you are interested in cloud computing? Awesome. Now, when it comes to cloud computing at a processor level, it is essentially just a privilege barrier. Okay. Now, this was now in ARM terms, because I don't remember the x86 terms. x86, I think there are rings, ring 0, ring whatever, right? So, in ARM terms you have EL0 exception level 0 which is user mode, exception level 1 which is kernel mode, and then there is exception level 2 which is hypervisor mode. Okay. So, now there is also something called as exception level 3 which is called secure boot mode, right. So, these are different privilege levels, and the idea is to never cross those privilege levels, and you always write code within those privilege levels, right. So, when you are writing virtualization hypervisors, you are writing it in EL2, okay. You are writing code that executes in EL2, and then when you want to execute a certain kernel, depending on which kernel it is from different guests in virtualization, you execute those in EL1, and then for user space EL0 for that kernel, that process. Okay. So, you have all of these levels of security abstractions for that very reason. So, syscall is one way to do it. There are similar instructions to switch between privilege levels between EL1, EL2 as well, and EL3. Okay. So, this was the smallest program that we saw. Now, to discover how these programs actually execute on your machine, right. Now, I showed you that main is not the first function that gets executed. It never was, it never will be. I had mentioned early initialization. I do not know if anyone actually noted that down. So, early initialization is essentially underscore init and whatever happens in underscore start. Okay. A bunch of things happen in underscore start, and then main is called. Okay. And those bunch of things, we will probably take a brief look at that. All right. So, the next thing we will get back to hello. Okay. And so, when you are looking at the static program, okay, let us look at, I do not remember which program this is. So, if I use the file command, so it gives me information about that program, right. So, what does it say? It says a 64-bit ELF LSB executable whatever version 1 statically linked. Okay. So, I have a statically linked program, all right. Now, if let me just build it dynamically, and I will call it hello.din. Okay. This is why -o is always important. You should always keep it. It is a practice, right. It is a very good practice to have. So, now I can compare them side by side. Now, this is dynamically linked, right. And here is the interesting thing, it is dynamically linked, and then the interpreter is this, and this is very, 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 very important. Okay. And it defines how your program is going to be executed. Okay. Now, do you know the system call that you would call to execute a program? The set of system calls. So, you have fork which creates a new process which is an exact image of the parent process, and then you call execve, right. So, what does execve do? Fork creates the similar image, right. What does execve do? Load the new program, right. So, it loads the new program in memory. So, where does this happen? Does it happen in kernel mode or user mode? And is loading the program sufficient? Okay. So, do you know the operation is called loading? And when you think of in system software, you have compiler, what is it? Compiler, assembler, linker, and then loader. Okay. So, now we are going to look at the loader. And the loader is not just one. Okay. There are two parts to the loader. Okay. The first part is the kernel, and for that I will open up the Linux kernel source. Okay. How many of you have downloaded this kernel source? If you haven't, you should go home and download this. And for every assignment, every concept, try to discover that concept in Linux. It's not that hard. Okay. So, in the kernel, there is something called as fs/exec.c, which is what provides the implementation for execve. Now, what exec.c does, and I expect you to like look at this once you get home or in your lab session, is that it loads the program and it starts reading the program. Okay? And the program is what? It is a file. It is a binary file, correct? And to be able to read a binary file, it needs to understand that binary format, correct? So, now if you look at fs, you will see bin fmt underscore star different files. Okay. Do you see a out over there? That is your a.out format from many years ago. Okay. Nobody has a.out format anymore, as in there are some maybe atomic reactor computers from the 60s or 70s which probably have a.out format binaries, but almost all of them today are in ELF format. Okay. So, the exec function will read using the ELF format decoder, okay. And the first thing that it will look for is whether the program has an interpreter or not. Okay. And this should blow your mind. You used to think that C was a compiled language and there is an interpreter for that, right? And it is a different level of interpreter, it is a different kind of interpreter. That interpreter is essentially the loader stage 2, as it were, okay, and that is implemented in glibc, right. So, if there is nothing of that sort, then it will look at the underscore start symbol inside that binary, and first it will look for the init section, run all the initializers, underscore start, and then start of the execution from there. Okay. So, it will transfer execution to that pointer in memory and go into EL0 and execute. Okay. So, that is fairly straightforward. It is when it finds an interpreter that things get a little interesting. Okay. When it finds an interpreter, it will execute the interpreter. It will load the interpreter in memory, okay, along with the binary, and then it will execute the underscore start of the interpreter. The interpreter does not have an, it has an init. So, it will do init, but it is very rudimentary, and then it will call the underscore start of the interpreter. And then from that, the interpreter takes over and it does a lot of very interesting things, which we will look at one by one. So, this was inside the kernel. Any questions here so far? None? All right. So, we will go back to glibc now. Now, glibc is where, so okay, there is a lot of stuff. So, there is a directory called ELF, which has, okay, this is also a lot of code. So, the ELF directory has the dynamic linker, okay, and the entry point for that is in a file called rtld.c, but the underscore start is architecture specific. Okay. So, it has to be written in assembly code. So, there is a file called dlmachine.h, which will be sysdeps. I will show you ARC64 because that is what I remember, but then there is an x86 version as well for this. Right. So, now remember that 4-line underscore start that we did? This is not very different there. So, this is your start. Okay. So, it is actually only this much, okay, and then it calls something, then dl start user comes in again, and essentially what happens is that the dynamic linker will then start reading the program again, okay, the program that you executed, all right, and it will start reading the library dependencies. It reads the libraries that the program needs. How do you find that out? You use a a command called LDD. Let's look at ls, since that is our favorite program today, right? If I say LDD, it says all of these programs it depends on, all of these libraries it depends on, right? So the dynamic linker does the exact same thing. It reads that binary, okay, and it reads all the dependencies. And what does it do? It loads each of those program libraries in memory, okay, and then for each of those libraries it will call its constructor, okay. And once that is done, once all of this is done, because now you can imagine there's a library in here which might be using another library as well, okay. So that becomes essentially a dependency tree. So it has to resolve the dependency tree. Once all of those have been initialized, then your program is initialized, okay, because it is assumed that your program cannot run without all of these libraries properly initialized, correct. A lot of things can go wrong over here. You can even have circular dependencies. In fact, there is a real circular dependency inside glibc. There is a library that implements threads. So the threads and libc proper are circularly dependent on each other, and we have some dirty hacks in place to make sure that they initialize properly. So you have like partially initialize in one place and then initialize the other, right? And then there's some redundant initialization which happens inside libc as well as libp thread. In any case, so all of this initialization happens, and then a function called libc start main is called, okay. And once that libc start main is called, that locates the main function inside your program, and it calls that main function. So after your main function exits, it comes back over here inside libc start main. Then it runs all of the destructors, and then it does the exit group syscall. So that's how your entire program executes. So it's not just your main, right? There are a lot of these things before and after, right? Any questions so far? No? Okay, great. So now we'll proceed to the next part, which is actually seeing your program in memory. So now you know how it is compiled into machine code. I assume you understand everything of that. If you don't, you ask me questions. Then from there, we looked at how it is loaded in memory, right? There's one command that you can very easily use to see how your initialization happens, right? So there's an environment variable called ld debug, and if I write file, if I assign file to it and I say hello, this is also why you should probably be using Linux when you're studying, right? Because there are a lot of things that you can just explore, and you can just start looking at the source code and try to figure out what is going on in there, right? So you say ld debug equals file hello. Once you do this, no files. Oh, this is a static one. Sorry. There. Okay. So what does it do? Let's just walk through this. Right. So hello is very, very simple. It uses only libc, right? So it sees libc.so.6 needed by hello.din, right? Generates a link map for it, meaning it parses libc.so, right? Then it looks at the parts of whatever. Then it calls init for libc.so. Then it inits hello.din. Then it transfers control, and then it calls fini, right? So if you look at something a little more complex like ls, it looks a lot bigger, right? So it looks at libselinux.so, then libpcap.so, then you have libc.so, libpcra2, dl, pthread, blah blah blah, and then so at this point it's created a dependency tree, and it's flattened that tree to make a sequence of initialization, right? and then it calls the initializers. So first one is pthread, then libc, then dl, pcre, da da da, and then finally bin_ls. Right? So all of these things happen first, and then your program executes. Right? Then there is something called as symbol resolution, which you can say all, and then it will look at all of the symbols. Okay. So symbols are essentially your function calls. So you called printf, for example, right? Now where is printf? Now you provided a declaration for it, correct? On one machine you provided a declaration for it and you were able to compile it. On another machine you were able to link it to a library, but now you want to run it on a third machine. What is the likelihood that printf is there? There is no guarantee, right? So what the dynamic linker does is when it encounters an unresolved symbol, meaning that symbol does not have an address in that entity, it will look in all of the libraries that it is linked to, libpcap, libc, pcre, dl, so on and so forth, and it will look for the first instance of printf. Okay, so the moment it finds the first instance of printf, it will record that address, and this is how relocation happens. This is how position independence works. The @PLT, that @PLT is essentially a table. It is a jump into a table. So that table is filled up, saying that, oh, I found printf. It is at this address. So whenever I'm jumping, I jump from here to that address. Then, right after that table has been filled. Now there's an obvious hack over here. Now, if you want to override printf with your own printf, all you have to do is write a printf function, build it into a library, and make sure that it is the first to load. Okay, so if it is the first in this sequence, okay, in all of these, so from libSE_Linux downwards, if it is the first one in that sequence, then your printf will be caught first. Okay, and this is called function interposition, and it is a very, very, very useful tool. In fact, all of your low-level debugging, function interposition is probably the most important tool that you should learn. Valgrind, vagara, everything is later. In fact, some of them even use function interposition as a concept to debug programs. Imagine if you want to gather statistics of how many times your program calls the printf function, or how many times your program calls the memcopy function, right? Let's say you are doing it in a loop, okay, and you want to gather statistics for that. You can use interposition for that, where you you make an interposition function which increments a counter and calls the real function. Okay, does that make sense? Great. Right, now we will move to actually visualizing your program in memory. Threads. Okay, so how many of you have written a multi-threaded program? Okay, so you've written pthreads functions, right? So we'll be writing a simple pthread program later. First thing is you need to figure out how your program is laid out in memory. How do you do that? There is a very, very simple way on Linux. There is a file system. It's a pseudo file system. It's an in-memory thing, structure that Linux abstracts, called the proc file system. Okay, the proc file system gives you a lot of information about your kernel. Okay, you can even tune the kernel using the proc file system. Okay, so the easiest way to find out or visualize how your program is laid out in memory is to read a file called maps. Okay, and this is a special hack where you say for the process ID, you say self, meaning yourself, whichever the program is. Now cat is the program over here. All right, cat is reading itself. Okay, and this is what cat looks like, and this is very big. Okay, yeah, right. And what is this? These are address ranges, permissions, and what file is on it. So now if you look at cat, cat not only has 3 different segments. So if you look at this, there are 3 different portions of memory for cat with different permissions. Not only is that in the address space of cat, you also have libc.so, you have something called as local archive, which I will not get into, ask me later if you want to, and then there is a dynamic linker, and then there is something magic here called stack, right. When you say stack was on RAM, it literally is there. It's this notional concept which is there in memory, right. And these are the memory address ranges within which it is there, and it is read write. Okay. And then there is something called as heap. What is the heap? Any guesses? What is the heap? From your CS class, I don't mind the definition as well. Textbook definition of a heap. Dynamic memory allocation, that's right. So heap is where you would do your dynamic memory allocation, right. So you would have constants and you would have global variables which would get allocated here, right, inside this. This is a read write segment in cat. Okay. So these are actual addresses. The 5563 A44 B 000 is an actual address. Okay. And it ends, it starts at that point and it ends at this point, and it has read write permission. Okay. And useful trivia, what are these addresses aligned to? You know what alignment is, right? What are they divisible by? What is the factor? Maths karo chahiye to on textbook and tell me the answer. See, all of them have 3 zeros at the end. Yeah. So what does that mean? What is the alignment? You probably need to write it down and compute it. So when you say 3 zeros, so what is the value 0xFFF? What is this value is what I want to know. And then what is the value 1000? And there's a very interesting bit of trivia over here, and the relevance of a term that you must have heard in your first year and then forgotten about. So what is this number in decimal? What are these numbers in decimal? 4095 and 4096. What is 4096? 4K, right? What is 4K? Ever heard of paging? Page sizes are 4K, right? So these are aligned to 4K, right? So now you know that these are in distinct pages. These are multiples of pages. These are multiples of page size, right? But then that is not the trivia I was talking about. This one digit or hexadecimal digit is how many bits? 8 bits? Is this 8 bit? 4 bits. What was 4 bits called? Nibble. When did you learn about nibble? First year? It was utterly useless, right? But now you know that if you see a nibble as 0, it actually means that it is 16 byte aligned. And you'll learn later on in life that 16 byte alignments are very, very important. As in, it's one of those holy numbers which you'll come across time and again when you're doing like computer architecture, right? So this is where nibble comes in useful, and this is why I imagine, I don't know for a fact, I imagine that people must have actually coined the term nibble to say that, oh, the lower nibble is 0, which means it is 16 byte aligned, right? So now you can actually use the word nibble somewhere and actually find good use for it. Anyway, so back to this. This is a very useful view of the program because you can now see where your global variables are, right? These are the addresses where your global variables are. And now this is a program that is already terminated, so it is not very useful, correct? Now you want to see this in a program that is always running. So let's try and do that. Quickly write this program down. And this is a very long program, so I'll give you a full 5 minutes to write this down. So what am I doing in this program? I have 4 includes, okay. Then I define a thread function called thr, all right. And all that the function does is sleeps for 500 seconds. Okay. Once you're done with this, I'll explain the main program, which is also very simple. So those who have done pthreads before can guess what is there in the main program. It just creates a thread and waits on that, waits on the thread. So this is pretty much what the program is. If you're done with the thread program, the program below is just this. It calls a pthread create and then a pthread join. The join basically makes sure that it keeps running, waiting for the child. Done? Return type for? Oh, so that is just a coding standard for formatting. So so because I contribute to glibc, so we have something called as a GNU coding standard, where we have the return type and whatever on one line, and then the function name, and then there's one space after that, and so it's basically what it does is it makes it easier for us to read code when we are because there's probably 20-30 of us across the world, right? Most of us don't even speak the same language, right? Writing the same set of code. So we want to make sure that at least there are no misunderstandings because of misalignment of code. So the coding standard kind of helps that. It becomes like this uniform body of code where you don't have to suddenly wonder where the opening brace went. You know where it's going to be at all times.
But then what if I had a comment?
That's fine. Yeah. That's the language parser aspect of it, right? So if you have a comment in between, the language parser should be able to identify that this is a comment block, ignore it, move to the next line. Okay, all set? Typed? How do you compile this? GCC -o and pthread. You can say -pthread as well. L is not required. That's a special thing for pthread. Okay, compiles as well. All right, not done. Done, right? So let me just quickly build this. So I say GCC -o threads and then -pthread, okay, or -lp thread is also okay. But then GCC actually identifies -pthread. All right, and now my threads program can just run in a loop. It will just stay there. Okay. Now in the next tab, I am going to try and analyze the thread program. First thing I need to do is find out its process ID. Okay. So I say pgrep threads, right? That is the name of the program. So pgrep tells me that the process ID is 10272. So now I can say cat proc 10272 maps, and this is my map for a running process. Okay. Is it okay? Do you want to see the program again? Oh, so the first thing I do is pgrep threads. Okay. That gives me a process ID. And then I say cat proc the process ID and maps. What is the name of a program? Is it running? Are you sure? You're getting two IDs when you say pgrep threads, right? Pick the first one. Are you sure you have not invoked two processes? That's fine. Pick the first one. Two in square brackets? Just two. What have you named it? Thread or threads? Thread. Okay, that's why. Then pick the bigger one, the second one. So pgrep is short form for PS, AUX and then grep, okay? Grep thread then gives me, there's threads and then there is thread D, which is a thread daemon, K thread D rather, which is a kernel process. You won't be able to read that, right? So you want your process. Got it? Okay, the second one. All right. So once you read this, now you can do something useful with it. So in this, now if you trap the program under a debugger and look at various variables, you'll find them within these address ranges. They're these actual address ranges. So you can even, since this is a user space process, you can actually try and modify variables and so on and so forth and see if there are any changes. Okay, so you can do some real interesting damage over here if you wanted to, right? But now what we want to do is we want to look at the map and try to figure out what is where and try to kind of map our OS theory classes to this. Okay. So this is your first one, right? So now every object that is there has at least three parts, right? So there is one part which is read and execute. Can you guess what is read and execute? It's code, right? Your code, whatever code you write, is going to be readable and executable, but never writable. Okay, so you don't accidentally write into your code. So your code section, the pages that are mapped are always only readable and executable. Okay, all of your global variables will be read write. So RW dash. Okay, your constants will be R. Okay, and then there is one page without any permissions. We will talk about that a little later. Okay. Then there is heap, where all the dynamic allocation happens, right? Wrong. So that is where a lot of the dynamic allocation happens. So there are two ways in which dynamic allocation happens, and it happens at different levels. So at the kernel level, there are two ways. One is in something called as the heap, which is this, okay? And then another way is something called as an anonymous map. Okay. Now if you look at this map, for example, this map is anonymous. It doesn't have any file backing it. Okay. These are called memory maps. Okay. So this memory map is anonymous, but it has read write permission. So, this is a dynamically allocated memory, all right. So, there are two system calls which do that. BRK system call helps you allocate in the heap, okay, and then there is an mmap system call which helps you allocate in a memory map anywhere in between. Okay. So, why do you need those two? So, have you heard of the malloc function? Right. So, malloc function is in glibc, okay, and it uses both. It uses heap as well as mmaps. Why would you want to use heap if you can use mmaps everywhere, or vice versa? So, one property of the heap is that it can only grow downwards, right. So, when you are allocating chunks in that, so that is what malloc essentially does. It allocates a chunk, it gives you an address for a chunk inside, and it returns that address to you, correct. Now, the problem is that when a chunk is stuck in the middle, you free it, and if you want something larger than that, you need to grow. So, you have what is called internal fragmentation. You must have heard that, right. So, the heap is susceptible to internal fragmentation. Whatever you allocate over there is susceptible to internal fragmentation. mmap is not. Then why not always allocate using mmap? That is a solution, right. We can always allocate using mmap, but there is a problem there also. What is the address, the minimum address size for this, or minimum page size, allocation size? It has to be one page, correct. It has to be one full page. It cannot be anything smaller than that. So, if I have to allocate 4 bytes with mmap, how much will I have to allocate? 4K. So, 4,000 whatever bytes is wasted. That is called external fragmentation. So, you must have seen that in OS class, right. So, now you see it physically over here, right. So, in malloc we have this heuristic where 128 bytes and above, for some cases we use mmap, 128 kilobytes, sorry, and anything lower we use the heap, and we do computations within the heap, right. And the other problem with mmap is that every time there is a syscall. To allocate also there is a system call, to free also there is a system call. Whereas with break, we can allocate at one shot, and then we can choose small chunks in there and return, right. So, that is one aspect of it. Now, the second aspect goes to the threads part of it. So, you wrote a multi-threaded program, right, and both of the threads are now running in parallel. They are currently executing, right. Now, what is the property of the thread? As in, what are the properties of threads? They have the same address space, correct. So, both threads have this address space. Both threads have this view of memory. Okay, that is what you see it as. This is the thread's view of memory. Okay, which means, or does it mean, you tell me, that this is the stack for both threads? Do two threads share a stack? No, right. So, this cannot be the stack, or is it a stack for one of the two threads? That is more likely, right. So, which is the other stack? So, the other stack is something that is dynamically allocated, and the way to guess it, and this is an educated guess that you can use only on Linux, nowhere else, is that every stack has a guard page on top. Okay. A guard page is a page that has no permissions. Okay. And the reason why you do that is if you have a stack overflow, the stack overflow should not overflow into the neighboring map. So, now for example, over here you have one guard page and read write anonymous map. Once again, this, right. So, now if this was not there, your stack would have overflowed into heap. So, now imagine you could have caused a stack overflow, and if you can craft it correctly, you can overwrite a specific variable in the heap. And that is a very powerful way to, that is essentially a bug that can be exploited as a security hole. right? This is essentially how most security exploits are written today, right? So, to protect against that, to protect against an underflow, you have a guard page, and with the guard page I can identify that this is the stack for the second thread. Okay. And similarly, you have something called as multiple heaps. So, in this there would be another heap, I am guessing over here, this or the other one might be a heap, right, because in glibc you have one heap per thread, and you can as you can engineer multiple heaps depending on the number of threads, so that you do not have to lock between threads, so they are faster, right. So, this is basically how you view your program in memory, whether you look at it from a debugger. So, when you are looking at it through a debugger, you are looking at only one part of it. This is a holistic view. This is what shows you the fact that your program is not alone. Your program has multiple libraries, your linker, loader, then you have a stack. You have something called as a VDSO, which I have not talked about. It's a very interesting concept. Your heap and your thread stacks, all of them are in there. Your thread control block, you must have heard of, right? Your thread control block is nothing but the lower part of your stack or the higher part of your stack, your thread stack. So, your thread stack has this structure at the bottom which has thread information, that is a thread control block, right. So, this is your view of a process. This is all the content that I had. What I would like to hear from you is questions, if you have any, in relation to this content or in relation to careers in tool chains, systems programming. I've worked with people right across the board when it comes to system programming, and I have done multiple roles, so I can answer questions about those as well. How to bypass the? The guard page, you mean? That is the guard page of the stack. It's not just a bit, right? So, like for your stack, there's an implicit guard page which is implemented by the kernel. This guard page, you mean, right? So, so attacks are typically how they work is you have buffer overflows, right? Like you have a buffer of size n, and you try to keep going beyond n, right? Or you have an underflow where you go under, right? So, the page as such, when you're going under, you will end up accessing something that has no access and then segfault without actually modifying anything. So, as such there is no way to get past it unless your increment sizes are more than the guard page size, okay, which is highly unlikely because your guard page is 4K, right. So, if you have a guard page of 4K and if you try to bypass, imagine you would rarely have an array which is like 4K structures and you are going like ahead by 4K. So, there is no real way to bypass that. So, is it an example that you are looking at, or as in do you have an actual example that possibly does it? Oh, okay, all right, yeah. So, no, there's no way to do that. That is the reason why it is engineered that way. So, there are other classes of attacks which can be used to do these things. Like you have, so this is just plain stack overflow which modifies this thing. Then similarly, there would be buffer overflows which could modify adjacent memory areas, right. Then there is something called as, there was a very famous vulnerability called return to libc, where if you look at the way your function prologue and epilogue is set, your return address is pushed onto stack. So, it is in memory, right. Now, imagine you have the return address on stack over here. So, this is your memory, right. So, you have your return address over here and then your local variables. Okay. If your local variable is an array that can override the return address, then I can actually put in the address to the a function called system. There's a function called system in glibc, which allows you to spawn different programs. So you can use it to spawn a shell, right? So I can just put system over here, right? And that will jump to the system function. And if I manage to set my registers or whatever the stack correctly, it can execute whatever the hell you want, right? The way they protected this was to introduce, so to make sure that all of the libc addresses have a 0 between them, so that the string processing terminates at that point. So there's return to libc as well. Then there's another concept called ROP gadgets, where you look at different snippets of assembly code and you try to jump between those. You basically reuse those snippets of assembly code. So Stack Overflow is just one way in which you can do it. And as technology evolves, we try to plug all of those one by one, like with guard pages, or there's something called as address space randomization. Like for example, your thread is running like this with these addresses, right? There was a time when the exact same addresses you would get at all times. So you knew which function was at which address from a statistical perspective, right? So with address space randomization, this kind of jumps about a bit. It jumps about enough that you cannot guess in any reasonable way that this function is going to be at this address, which is also a very powerful mechanism to defeat vulnerabilities. Then there are hardware vulnerabilities, but that's a different thing altogether. Have you heard of Spectre and Meltdown that happened earlier this year? Yeah. So that is like a class in itself, and it's fun to read those vulnerabilities. Anything else?
One question that I had in the afternoon was how do people open source make
So
I guess that so guys are a little shy. So
okay.
I'll ask on their behalf.
Okay.
How does one look at a career in open source?
Right.
One make enough money or whatever? How is the job of buying?
So there are two aspects of it, right? How do businesses make money on open source, right? And then how do open source engineers make money, right? So open source businesses, most of them make money from. So there are two ways. One is the Red Hat model or the Linaro model, where we make money out of services, right? Like Red Hat makes money out of support. And it's not just like technical support, call center, it's not that sort of thing, right? I started in tech support in Red Hat, by the way. It's more of, I want feature X in this compiler, right? And I want it to be done yesterday, and somebody has to work on it. And consequently, somebody has to work on it so that somebody gets paid for it, right? Like for example, a bank which has a very performance sensitive trading system, and this is an actual example where I'm anonymizing bits, right? Where the hot code, as in the most performance sensitive code, is 5 instructions when it should have been 3 instructions. So somebody actually needs to tweak the compiler pass to make sure that those 5 instructions are that sequence as such is recognized, and 3 instructions are generated instead of 5, right? So that's where our job opportunities come from, and those job opportunities are never going to die, right? Because we are looking for faster and faster, better and better performance as years go by. We have newer processors that come in. We have newer programming languages that come in, right? And everyone wants to be able to support that. So the second part is hardware manufacturers, where hardware manufacturers have their own compiler teams, have their own technical teams, and they cannot like develop and maintain their own toolchain at all times, because whatever you say, maintaining your own toolchain is a very expensive effort. It's an extremely expensive effort. It is the reason why Intel, though it has its own ICC compiler, it is fast trying to move towards LLVM. It is very, very involved in GCC development for that very reason, because they cannot do all of the maintenance. So what open source, the ecosystem essentially does is it ends up dividing the maintenance cost between different companies, right? Nothing happens for free. In fact, if you look at the list of contributors in glibc and GCC, a huge bulk of them work for a company for that reason. They're maintaining glibc, they're maintaining binutils or GCC, parts of it, improving it for a company. It is never a hobby project, right? It starts as a hobby project, and it almost inevitably, because we have such less compiler engineers, it almost inevitably becomes a profession, and it is a very, very lucrative profession. I can tell you that as well. As in, you can think ML, AI, and all of that. They're not nearly as lucrative as compilers is. So yeah, so money is the least of your issues. If you're working in tool chains, definitely if you're working in open source, money is the least of your issues, because open source projects in general are under maintained, and companies are always looking for people to hire to maintain them so that they look good to their customers. So there is like a full robust economy around it. Okay. Any other questions? Questions to this effect are also fine. Great. So hopefully this was helpful, and thank you for your time, and happy to be here.